Hello, my name is Carson Roberts, and I will be talking about soil amendments in agriculture. Before I get started, I'd kind of like to talk a little bit about where I'm from. I grew up in Idaho. I've worked with agricultural crops in 8 different states, and I've worked with I've grown over 15 different crops in the course of my career. And I've worked a lot with soil amendments. I've worked at co-ops and with chemical companies dealing with soil amendments of all different kinds. So I have a pretty wide range of experience, but I drew most of my information today from a book. So if you have this book, some of you might have it. It's Soil Fertility and Fertilizers. If you don't have it, I'm sure there's a copy at the university library. So go ahead and look at that if you have any questions about what I've talked about today, because it's in that book. Okay, so soil amendments in agriculture, what do they do? And I found a definition: soil amendments improve the physical or chemical properties of the soil. And an important question to ask is why do soils need amending? Because amending essentially means that something is missing or broken. So why do our soils need amending? And I'd like to start with an example of wheat. Wheat is a very, very common crop that's grown, and it's one of the oldest crops that has ever been cultivated. And man and wheat have kind of evolved together over the course. It's one of the main nutritional or dietary supplements for people. Very common, and so in an average yielding field across the United States, about 50 bushels per acre. And with 50 bushels per acre of wheat removed from the field, that's the wheat grain itself, we are removing 75 pounds of nitrogen, pounds per acre. That's a horrible 75 pounds per acre of nitrogen. Okay. 30 pounds, pounds per acre of phosphorus, and 17 pounds per acre of potassium. Okay, that's for the average field in America producing average yields. That's how much nutrients are going to be removed, and these are the major nutrients: N, P, and K. There's also a bunch of others that are removed as well, but this is what is in 50 bushels of wheat. And this wheat is then eaten by people. And it's moved off, made into bread, made into pasta, made into a bunch of other crops. So, this is actually, so wheat's a pretty conservative too, because other crops take way more, especially crops like alfalfa takes a lot more. I know that alfalfa takes about 400 pounds of N and at least 100 pounds of P and about 100 pounds of K per year. So that's a large amount, but that's another different crop that's grown, for example. And all of this comes from the soil. None of this can be taken up by the atmosphere. There's atmospheric N2 gas, but plants can't take it up. And so another thing to remember with why soil needs amending, here's one thing. Crops are taken off the field. but there's also another, and I'd like to show an example of this. And this will be called my diaper example. So a lot of people can think of soils like this. This is the run-of-the-mill disposable diaper, right? A lot of people think when you put inputs into the soil or put inputs into the diaper, we're just basically going to put them in there, right? And the soil's going to catch all that and it's going to hold it. Just like a diaper holds all that in there. That's what a lot of people think the soil can do. But that's not necessarily the case. Soil isn't really like a diaper. Or at least not this diaper. It's more like this diaper. This is a cloth diaper. This is what our ancestors used. I think may have been what I used if I was old enough, but I don't know. I haven't asked my mom yet. Anyway, this is a cloth diaper. Watched on YouTube how to fold this up, but let's put some water in this one and see what happens. Okay. Oh, see that? Put a little more in there. Oh boy. So this diaper is inherently leaky. It's kind of like our soils. They're leaky. Things run out of them. Things run off of them. And things can get into the atmosphere from here. Unlike that diaper, and you've seen the moms, they pull the diaper off so that they can smell and see if it's stinky, right? With this one, you don't have to pull the diaper apart to smell because you know when it's stinky. This is more like a soil than that. The diapers that we know today. So that's my diaper example. So with those two things, nutrients coming off one way, nutrients leaving the field by leaching through the soil or running off or evaporating into the atmosphere. Those are all different ways that nutrients that the plant needs, that the plant takes up, that need to be replaced in order to grow a crop, right? So for a soil like this, even though we only took 75, because of these inherent inefficiencies in a soil, we may need to put on a little more than that, maybe 80 or 90 or maybe even 100 if we have a really inefficient soil, so that we can get the 75 pounds of nitrogen into the wheat plant. Okay? Let's see. Okay. Now, let's talk about some essential nutrients. And as I do this, I'm going to start with chemical fertilizers. So let me erase all this. Okay. So, chemical. Oh boy. Fertilizers. Okay. And I don't really like the word chemical for fertilizers. I would prefer mineral. Mineral fertilizers, because they're not really chemicals. Most fertilizers are naturally found in the soil, or the composition of those fertilizers is found in nature. And there are a lot of these products out there. And let me go grab a couple of those. Okay, I have a couple of these examples of fertilizer here that I stole from the lab today. And first, I'd like to talk about nitrogen. I'll mostly talk about the three main elements because because they're the ones that we most commonly put on. So let's talk about nitrogen first. Nitrogen is taken up mainly in the plant in the form of nitrate and, oh boy, this marker might be dying, NO3. Okay, that's one of the forms. And then NH4 positive. Okay, so we have a cation, ion, anion, and these are both taken up by the plant. The plant prefers to take up ammonium, but it will take up nitrate. It's not that much harder. So these are the two forms that they're taken up, and there's a couple of fertilizers. The most common one that you'll see is urea, and this is a white prill, and this one would be more on the chemical side. It's a CONH2 formula, but it is very quickly turned into it very quickly turns into ammonium and nitrate in the soil. So there's urea, and urea, along with a lot of these other nitrogen products, we know that they're very easily evaporate or volatilize, and they very easily leach. And so we have come up with some products of urea like this one. This is a polymer coated urea. They call it ESN, or environmentally smart nitrogen. So here's another nitrogen product. And then there's one more that I want to show you. This is AMS, so ammonium sulfate. Both ammonium and sulfate are plant available forms of nitrogen. So even though this is chemically produced, it is plant available. So that's AMS. It's a pretty good product, but it's not as cheap as urea because the process is a little different. There's a ton of different fertilizers. I'm just scratching the surface on some of these. And then let's go to phosphorus. Now, phosphorus is a little different animal, but it only has a couple of forms also that it'll take up. And the first, oh boy, H2PO4 negative and HPO4 negative 2. So these are the common forms of nitrogen that a plant will uptake. Plants don't like to take up any other form. So if it's in a different form, organic forms, for both of these, if either of these are in organic forms, the plant can't take it up. It has to be mineralized by microbes in the soil before the plant can take it up. So let's look at one of this. This is monoammonium phosphate. And so it has nitrogen in it. It actually has ammonia, so it's an NH4H2PO4. So H2PO4. This is naturally available to the plant, or available to the plant. That's how it naturally takes it up. And we also have an NH4, which is an ammonium product. Just the process of making monoammonium phosphate is how some of that nitrogen is there. So that's phosphorus. Now, let's get into potassium. Potassium is only taken up in one way, and that's as it's in its ionic form of K positive. And this is a pretty potassium is by nature it kind of stays in this form, and it usually bonds to a lot of things like chlorine or clay particles. So this mineral form, this is potassium product 0060, and its formulation is KCl, or potassium chloride. And if you look at it, it looks like a bunch of little pink rocks, which is really what it is, and it's quite salty. So when people are working on applying this to fields, you can't apply it in doses over 200, or else it'll burn the crop because there's too much salt in it. Okay, so those are some of the common mineral fertilizers. Don't want to really call them chemical because a lot of these formulations are found in nature. Okay, so let's move on to a different kind of ag soil amendment. Okay, erase all this. Okay, so let's move on to this other soil amendment, biosolids. Okay, biosolids, under this umbrella, we would have things like manure, animal manure, let's see, compost, wastewater, and then there's a whole gamut of different other ones like biochar, for example. And with this biochar, here comes an often a fallacy that I have heard often is biochar is a carbon product. There's not really any mineral fertility value to it. And one of the common fallacies that I hear a lot is that carbon is a fertilizer. Well, no, it's not. It can't be taken up by the plant. This biochar is more of a soil amendment for the soil. They try to use it to increase water holding capacity, or to increase buffer capacity, or to increase cation exchange capacity in the soil. And that's with pretty much all carbon inputs that you can put on the soil. Plant can't take them up. It's for the good of the soil physical property. The problem with something like biochar is that usually you can't put enough of it on to make a difference, because the soil is this vast ecosystem of underground things, and there's so much under there that the little amount that we can put on, economically can put on, can't really make a difference. But manure, compost, wastewater, these are all byproducts of another operation, and they can be put on economically, and sometimes it's more economic to put them on than say a mineral fertilizer. And personally, manure is my favorite soil amendment because of all the great things that it does to the soil. It's really a good soil amendment if you can get away with it. But let's go ahead and use an example. Now, all of these differ in the amount of mineral composition of different elements that are in the biosolid product. So, for example, I'm going to do some poultry litter. Poultry litter, and it is it is 33% nitrogen. Oops, that's an M. Nitrogen, and 48% phosphorus, and 34% potassium. in an average poultry litter, it really depends on what diet they're feeding, how much nitrogen has volatilized, and maybe this is even a generous number for the amount of nitrogen that can be in poultry litter. So with this, there's one thing, and this is very important to remember, is that the nitrogen to phosphorus ratio is off in most manure products for a crop. For example, we had our wheat example, and wheat needs 75. Oops. Oh boy, our marker may have died. 75 pounds of nitrogen, and it needs 30 pounds of phosphorus. So notice how it needs a greater amount of nitrogen than it does phosphorus. So if we apply poultry litter to amend for a crop like wheat, we are going to apply way more phosphorus if we apply to meet the nitrogen requirements of that plant. And so there will be way more phosphorus than what the soil needs, what the plant needs. And this becomes a problem because this is subject to leaching. It's subject to running off and getting into places where it shouldn't be. And especially in fresh water, phosphorus is usually a limiting factor for things like algae. And so algal blooms in fresh water can go really crazy over this, create some hypoxic zones and stuff like that. So that's one very important thing to keep in mind ecologically with products like manure and compost. They're often phosphorus is the largest thing. So if you're going to apply this, you would apply for the phosphorus rate and then amend some other way for the nitrogen so that you don't overload on phosphorus. Okay, let's move on to another type of amendment. And for lack of better terms, let's erase this. Lack of better terms, I'm going to call this one, come on. My marker may have completely died. All right, let's see if we can't grab a different one here. I think I have it here somewhere. Or not. Oh, here it is. Okay. Maybe this one will work better. Living amendments. Oh boy, I spelled it with two M's. Amendments. Okay. That's not any better, is it? Well, shoot. Anyway, well, we're just going to have to, maybe we can go find a different one or something. Okay, living amendments. There won't be much writing on the chalkboard anyways after this. So, living amendments do great things. They, one of the things, for example, with the living amendment, I don't really want to get too far down this rabbit hole without explaining this, is cover crops. So, well, that's not going to work. We're just going to have to forget this. Okay, cover crops are an example of a soil amendment. Why can they be classified as a soil amendment? Well, that's their job, is to fix broken soils. So cover crops can improve soil structure. They can improve infiltration. They can improve water holding capacity, and they can improve issues like compaction and stuff like that. There's been a lot of research done with cover crops and their abilities in improving and amending soils. And another task that cover crops can do is fix nitrogen through legumes. But I'm going to put legumes under a different category because we can gain nitrogen from legumes from rotating crops and from using them as cover crops. Usually a crop rotation works a little better because more nitrogen is available to the cash crop. So an example of a legume is alfalfa. That would be the main one that we use worldwide, really. Alfalfa is the number one crop, and it can give up to 100 pounds of nitrogen per acre in the year after the crop is rotated out. And they fix atmospheric nitrogen or N2 gas. They themselves don't fix it though. The Rhizobia bacteria, their relationship with Rhizobia bacteria, the Rhizobia fix the nitrogen. And this brings me to an often thought fallacy with legumes, and that's that legumes, and I've heard this a number of times, and it's a very common fallacy, that when legumes are planted with grasses or intercropping, and you may have seen this, especially if you pay attention to a lot of the soil health stuff, but a lot of this, so fallacy, when legumes are planted with a grass or a non-nitrogen fixer, the legumes will share nitrogen with the grass or non-nitrogen fixing crop. And that is not true. Legumes don't share. They're like most other critters. They don't share their food at all. They and the Rhizobia pretty much keep it all and use it all for themselves. Now, where other crops can or other plants can get the benefit of a legume is when the legume either dies or is eaten by something and defecate, and the nitrogen is then defecated onto the soil surface, and then the plants can take it up. So, for example, in some grazing studies, they found when they were working with some legume crops, they found that no nitrogen benefit comes in the first year, and little nitrogen benefit comes to, say, a grass, unless there's an animal to consume that and recycle the nitrogen and place it into available form where another crop or another plant can take it up. Another thing with legumes is a lot of people think legumes don't need fertilizer. They do need fertilizer. Like I mentioned earlier, a crop like alfalfa uses a lot of phosphorus, about 100 pounds per acre per year. And that is a lot. So this leads me to another living amendment, and that is livestock or animals. Because, like I said previously, they recycle these nutrients and put them, hopefully, back into the system. But we need to remember that this is not a perfect cycle. When an animal, and you could even include humans into that, when we eat something and then release the nutrients in an available form, oftentimes, especially with urine, that nutrients, or especially nitrogen, is volatilized before it can ever reach the plant. Sometimes volatilization, especially if it's a warm day, in urine, it can happen in like 15 minutes, and all of the nitrogen that was available in the urine can be evaporated into the atmosphere. And so that's kind of an unfortunate fact. Another issue with plants in this, or with animals in the plant system, as far as a soil amendment goes, is that as is the nature with most animals, we eat in one place and then they go to another place to defecate and to eat. So for example, turkeys, they'll go eat somewhere, and then when they go to roost, they'll let all that out in an available form in their roost instead of where they took it from. We humans, we do the same thing. We eat in the kitchen and then we go to the bathroom and release all that nutrients there. Ruminants do the same thing also. They'll go out and eat in a pasture during the morning time, and then they'll go into a shady spot during the day and spend most of their time there. And so that's where most of that nutrients ends up, is in a shady area. So it's not a perfect system. So that's pretty much it. I could probably go on with some other living organism amendments, but we'll move on to biological amendments, and there's a bajillion of these products out there, and so I don't really have I don't really want to cover them all because there's just so many. But we have things like algae and seaweed and some unknown concentrations of things, and things like free-living rhizobia bacteria and biostimulants. These are all things that are products amendments that are sold on the market. It's really difficult to know if they work or not. There's been tons of research done, and I've even done some research on a number of products like this, and it's hard to find differences between treating soil with these amendments or not. So it's important to be wary with these because they may not work. Okay. So in summary, soil amendments are necessary as long as we keep transporting those nutrients in the form of food away from the place where the food was grown. And let's remember also with this that we have this diaper effect here too, where some of the nutrients that a plant may need may leak out of the system in one way